To find the position and velocity of something like a volleyball would be pretty simple. With just a little knowledge of classical physics, you could simultaneously calculate both values at any given time on its path. But what happens if the volleyball is instead an electron? Long story short, it's simply not possible, and objects on the subatomic scale don't have precise positions and velocities at the same time. Welcome to the weirdness of the quantum realm and the Heisenberg Uncertainty Principle. In 1927, physicist Werner Heisenberg, no, not that Heisenberg, discovered that there was an intrinsic limit to how precisely one can measure the position and momentum of subatomic matter at the same time. Gaining precision of its momentum literally means losing precision of its position, and vice versa. The principle arises not from faulty measuring devices or the act of observation, but the fact that everything around us exhibits both wave and particle properties. From light and electrons to me and you, everything behaves like a wave and a particle. But it's only at the subatomic scale that the wave nature of objects is noticeable, and it is the distinct differences between wave and particle properties that causes this trade-off of knowledge. A wave is spread out over space, meaning it doesn't have a precise position. However, it does have a momentum, as defined by its wavelength, the distance between two of its peaks or valleys. A particle, on the other hand, does have a position, which means its exact location in space is known. But it doesn't have a wavelength, so its velocity and momentum are undefined. So in order to know the position and momentum of something like an electron, it would have to be localized like a particle and have a wavelength like a wave. This is achieved by adding multiple waves together of different wavelengths and amplitudes, and through the magic of wave interference, a wave packet is formed. This packet is localized and has a more defined position, but some uncertainty still remains. On top of that, the wave packet consists of many wavelengths now, meaning the exact momentum and velocity of the object is uncertain. As you add more waves to the wave packet, the position would become more and more defined, but you would be completely uncertain of its momentum. It's almost like trying to pay full attention to both the TV and my English essay that's due in 30 minutes. It's impossible. As I put more attention towards the TV, I'm forced to pay less attention to my essay. However, unlike my failure to multitask, the uncertainty principle is built into reality and reveals that the universe isn't as deterministic as we thought it was. The questions we ask and experiments we perform determine how nature responds. As Heisenberg himself put it, what we observe is not nature itself, but nature exposed to our method of questioning. The Newtonian clockwork that we once thought ruled the universe doesn't seem to be completely true after the development of modern physics. But there are still so many questions in quantum mechanics that are still waiting to be answered. Are there an infinite number of universes? What does Schrödinger's equation even mean? Who knows when we'll find the answers to these questions and the hundreds more I'm sure we'll have. But it's up to us to make sense of the seemingly unexplainable theory of quantum mechanics that our predecessors so kindly developed. Thanks for watching.